Okay, so we have a physics PhD qualifying exam, practice problem number 6 in classical mechanics. So we're going to consider the Duffing oscillator, where this absolute value epsilon is much less than 1, x double dot plus omega naught squared x plus epsilon x cubed equals 0. Okay, so for part A, determine the conserved energy. So this is a nonlinear oscillations problem, and for the conserved energy here, for the Duffing oscillator, x double dot plus omega naught squared plus epsilon x cubed equals 0. For where epsilon is much less, absolute value of epsilon is much less than 1. We can view it as a unit mass particle moving in a nonlinear potential. Start with x double dot plus omega naught squared x plus epsilon x cubed equals 0. From there, we'll multiply by x dot. So we're going to wind up with x dot, x double dot plus omega naught squared x, x double dot plus epsilon x cubed x dot equals 0. Recognize each term as a total derivative. So here d dt 1 half x dot squared plus d dt 1 half omega naught squared x squared plus d dt 1/4 epsilon x to the 4th equals 0. So we're going to get E equals 1 half x dot squared plus 1 half omega naught squared x squared plus 1/4 epsilon x to the 4th is conserved. And the potential energy is going to be V of x equals 1 half omega naught squared x squared plus 1/4 epsilon x to the 4th. Okay, that's for letter A. For letter B, using perturbation theory, determine the first order correction to the oscillation. So for letter B, first order correction to the oscillation frequency. So assume a solution with amplitude A here. X of t approximates A cosine capital omega t, cosine of capital omega t, and let tau equal capital omega t. Then x double dot equals capital omega squared, second derivative of x with respect to tau. Okay, so the equation becomes capital omega squared x double prime plus omega naught squared x plus epsilon x cubed equals 0. And to first order, we're going to use x as approximately a cosine tau, and then x cubed equals a cubed cosine cubed tau. And using cosine cubed tau equals 3/4 cosine tau plus 1/4 cosine 3 tau. The equation contains a resonant cosine tau term. And to avoid, to avoid secular growth, the coefficient of the fundamental harmonic must vanish. And we have negative capital omega squared a cosine tau plus omega naught squared a cosine tau plus 3/4 epsilon a cubed cosine tau equals 0. So negative capital omega squared plus omega naught squared plus 3/4 epsilon a squared equals 0. And here, isolating that omega squared, that equals, isolating capital omega squared equals omega naught squared plus 3/4 epsilon a squared. And therefore, to the first order in epsilon, capital omega is approximately omega naught plus 3 epsilon a squared over 8 omega naught. And also equivalently, delta capital omega over omega naught is approximately 3 epsilon a squared over 8 omega naught squared. Okay, so that's for letter B. And just going back here for letter C. Letter C wants us to determine whether positive epsilon corresponds to a hardening or softening spring. Okay, so for letter C here, hardening or softening spring. The corrective frequency is capital omega, is approximately omega naught plus 3 epsilon a squared over 8 omega naught. If epsilon is greater than 0, then capital omega is greater than omega naught. So the oscillator frequency increases with amplitude. This is called a hardening spring. If epsilon is less than 0, then capital omega is less than omega naught. So the oscillator frequency decreases with amplitude. This is a softening spring. Therefore, epsilon greater than 0 gives a hardening spring. Epsilon less than 0 gives a softening spring. Okay, so that's letter C. Going back here for letter D, determine the amplitude at which the perturbative solution ceases to be accurate. So letter D. Okay, so for letter D here, amplitude where perturbation theory ceases to be accurate. Well, perturbation theory assumes the nonlinear term is small compared with the linear restoring force. The absolute value, so absolute value epsilon x cubed, much less than omega naught squared, absolute value of x. And for typical amplitude A, absolute value of epsilon a cubed is much less than omega naught squared a. Cancel, a cannot equal 0. Absolute value of epsilon a squared much less than omega naught squared. Thus, perturbation theory is reliable when a is much less than the quotient of omega naught and the square root of the absolute value of epsilon. It begins to fail when a is proportional to omega naught over the square root of absolute value of epsilon. So, for epsilon is greater than 0, this means the quartic potential becomes comparable to the quadratic potential, and for epsilon is less than 0, this is also near the amplitude where the potential develops escape behavior. Okay, that's for part D. Now moving along for part E. For part E, describe the phase space topology for positive and negative epsilon. Okay, so for part E, phase space topology for positive and negative epsilon. The phase space curves are level sets of E equals 1/2 x dot squared plus 1/2 omega naught squared x squared plus 1/4 epsilon x to the 4th. The first case, case 1, epsilon greater than 0, the potential is V of x equals 1/2 omega naught squared x squared plus 1/4 epsilon x to the 4th. Both terms are positive, so V of x, that's approaching positive infinity as absolute value of x approaches infinity. Therefore, all finite energy trajectories are bounded and closed in phase space. So for epsilon greater than 0, all phase space orbits are closed curves. All phase space orbits are closed curves around x comma x dot equals 0 comma 0. The curves are distorted ellipses becoming more sharply confined at large x. So that's case 1. Moving along now to case 2. Case 2, epsilon is less than 0. If epsilon is equal to negative absolute value of epsilon, then V of x equals 1/2 omega naught squared x squared minus 1/4 absolute value of epsilon times x to the 4th. The potential has a stable minimum at x equals 0, but unstable maxima where derivative of v with respect to x equals omega naught squared x minus absolute value epsilon x cubed equals 0. So x equals 0, or x squared equals omega naught squared over absolute value of epsilon. And unstable points are x equals plus or minus omega naught over the square root of absolute value of epsilon. The energy at this point, at these points, is E sub SEP equals 1/2 omega naught squared times omega naught squared over absolute value of epsilon minus 1/4 times absolute value of epsilon times omega naught to the 4th over absolute value of epsilon squared. Okay. Also here for this separatrix energy, that E sub SEP equals omega naught to the 4th over 4 times absolute value epsilon. So we could say thus for epsilon is less than 0, small energy trajectories are closed around the origin, but above the separatrix energy the particle escapes to large absolute value of x. So we get the following. E less than epsilon gives closed orbits only inside a separatrix. Outside the separatrix, trajectories are unbounded. Okay, so that's letter E. Now moving along to letter F. Just going back to read here on the first page. Discuss. Letter F, discuss the physical significance of amplitude-dependent frequencies. Okay, so letter F, last one here, this problem. The physical significance of amplitude-dependent frequency. For a linear oscillator, x double dot plus omega naught squared x equals 0, the frequency is independent of amplitude. Every oscillation has the same frequency, omega naught. For the Duffing oscillator, the frequency depends on amplitude. Capital omega is approximately omega naught plus 3 epsilon a squared over 8 omega naught. Large amplitude oscillations do not behave like small amplitude oscillations. For epsilon greater than 0, larger oscillations are faster. For epsilon is less than 0, larger oscillations are slower. Physically, this leads to nonlinear effects such as frequency shifts, distortion of waveforms, amplitude-dependent resonance, nonlinear detuning, and eventual breakdown of simple harmonic motion. So, nonlinearity makes the oscillator frequency depend on energy and amplitude. Okay, so that's all for this problem. Thank you very much and have a great day.